Hello everyone. What we're going to discuss in this lecture is Bragg diffraction. We will also discuss some general aspect of diffraction grading at the end of this lecture. Okay, so Bragg diffraction. So why is this important? Well, you studied the diffraction grading physics in previous lectures, and what we said is that if you make rulings, if you can make these lines patterned on a very highly reflective surface, then you can make a monochromator. But guess what? There's a limitation to what people can do at this point in terms of making these rulings very, very high quality and very, very many rulings in a significant area. So what happens is that you can make these rulings with slit spacing, let's say 1 micron or 100 nanometer, real easy. All you have to do is to pay money, and then they will make it for you. However, if you want to create some monochromatic X-ray light, or then it's an entirely different matter. Why? Because X-ray light, their wavelength is on the order of 1 angstrom. X-ray light wavelength is on the order of 1 angstrom. So then the diffraction grading that you need needs to have a spacing which is which is slightly larger than the lambda value. So maybe 10 angstrom, a few tens of angstrom, and things like that. That's a very challenging thing to do. We don't have a good technology to create structures with a regular spacing like 1 angstrom or 10 angstrom scale in a large finite area. So this is, let me remind you what is angstrom. That's the 10 to the minus 10 meters. It's basically the atomic size. Remember, the hydrogen atom has a radius of about 0.5 angstroms. So what do we do if we want to monochromatize and generate a very high quality X-ray beam? The fact is, high quality X-ray beams are generated every day by scientists at, for example, Advanced Photon Source in Illinois, near Chicago, or up at the Hill and in Berkeley, Advanced Light Source, and Brookhaven and places like that. But how do people do that? Well, nature has given us this thing called crystals. Nature has given us this thing called crystals. And these crystals can be thought of as it's a beautiful object to imagine, and beautiful object to look at if you can find a big crystal. What it is crystal is nature's gift to us in the form of basically infinite diffraction gratings in one. Gratings in one small crystal that you can hold on your palm, can be thought of as an an infinite number of diffraction gratings. So let's think about why this is. So let's say that you have, as a simple example, let's say that you have a crystal which is a boring kind of crystal, which is okay for a pedagogical purpose. So what we're going to make is we're going to make a square array of circles here, and circles represent the central position of atoms. So let's say that you have this two-dimensional arrangement of regular square crystal. And this goes on, this goes on for quite a bit. So let's actually discuss, if you have a small crystal on your hand, for instance, let's say, what's the size? Well, let's be very modest. Let's be very modest and say the size here, typical dimension here, is about 1 millimeter. It turns out scientific crystals, the smaller crystals, tend to be better quality. If you have a large crystal, you can grow a very good quality crystal, large, but it's extremely hard. Large crystals tend to be composed of multiple crystallites and so on. So 1 millimeter is actually a typical size of crystals in scientific experiments. So anyway, so let's say you have 1 millimeter, and what are the typical dimensions? The atomic spacings in a crystal. Atomic spacing is about 3 angstrom. Well, it could be 5. It could be 2. It could be as large as 10 sometimes. But anyway, 3 angstrom is very common. So then you can figure out, how many atoms are aligned in this direction. How many, And so, so you can say 1 millimeter by 3 angstrom. How many atomic layers are in one direction? So that's 1 millimeter is 10 to the negative 7th meter. So that's 10 to the negative 5th centimeter. So 10 to the negative 3 meter in the SI unit. This is 3 times 10 to the negative 10. So that means this is about 3 times 3 million. 3 million layers. So this is on the order of n. So remember in the diffraction grating physics we talked about number of rulings and stuff. So number of rulings or number of slits, n. If you just hold a small crystal on your hand, 1 millimeter, you got 3 million rulings made for you by nature. Well, it's not just that. You get infinite number of those diffraction grating. But what do I mean by that? So let's see what I mean by that. So that in order to appreciate that, you need to understand what's a crystalline plane, crystal planes, and things like that. So let me, without going through the whole crystallography business, let me actually give you 2 examples of crystal planes. So if you have this kind of square crystal, you can say, well, where is a plane? So then you can say, well, this is one plane. Oh, sorry, I didn't. I meant to change the color. A second. Yeah. So let me change the color. So you can say, okay, so this is an atomic plane, and then there is another plane. And then there is another plane, the same plane. So notice that these red planes are identical planes. They are just shifted by a certain displacement Otherwise, they have the same orientation, they have the same composition. So these are called crystalline planes, crystal planes. But that's not the only way that you can make a crystal plane. Let me actually make a blue plane. So what you do is, well, you can make a diagonal plane. Well, that's too obvious. Let me be a little bit weird. Let me draw a diagonal, which is kind of not connecting the nearest neighbor diagonal points, but the next one. So what you do is you can make a connection like this, and this guy will have another pair down here, which I didn't have space to draw there, but there is that crystalline plane. And then this guy, look at this, and then this guy will have a partner here, up there, and I didn't have space to draw that, so there's another plane. You can see that my drawing skill is severely challenged, but maybe you can see, you should be able to be convinced that these crystalline planes are again all identical. They are identical composition-wise. They are identical orientation-wise. They are just shifted by this spacing. And if you think about it, this set of red crystal planes, or actually the more correct name is lattice planes. This red lattice plane, there's a red lattice plane, and then there are these blue lattice planes, and can you see that there are actually infinite ways of making this coming up with different lattice planes? For example, you can connect these two diagonal lines and then go on make. There is one possibility like that. And you can also go in this other way, or you can go connect this point to that third farthest diagonal atom, and then you can keep on doing that. And there's no limitation to this. So they're basically infinite. If the atom in a crystal size is infinite, then you basically have infinite ways of doing that. Of course, crystal is not infinite, but in this case, in this example where there are 3 times 10 to the 6, 3 million atomic layers, basically what you have is the same order. You have million different lattice planes that you can form. I mean, not exactly million, but on the order of a million. So that's the meaning of these infinite diffraction gratings. So infinite diffraction grating means when as n goes to infinity. So there's and it turns out this is also on the order of n. It's actually not n. N here n is also only in the one direction, right? So the atomic layers are how many atoms that you have? The number of atoms are basically n to the third power. So diffraction grating is n to the cubed, n cubed, and so that's that's a lot of lattice planes. So I hope you got the point. There's one grating here. There's another grating here. And basically you get an infinite number of gratings there. So now let's look at the two lattice planes that we made here. So let's say this is D. And then for the blue lattice planes, this is another D. So you can see that this D is different from that D, and then their orientations are different. That's the key. Because the spacing is different, you can these are two different gratings, and because the orientations are different, depending on how you orient your crystal, you can make use of this grating, the red grating, or the blue grating, or any other one of the gratings that you find in the crystal. So that's how it goes. So in a lot of experimental facilities, people use crystals. A prime example is a silicon crystal, and they make highly monochromatized X-ray light using those crystals. So now let's do the theory here. The theory is very simple. I'm going to do the theory with respect to this. Actually, let me do it here. So I hope you agree with me that the whichever lattice planes you take, basically what you have is planes of atoms with distance d. So that's like diffraction grating, except that in the diffraction grating we had rulings made on a surface. So those are one-dimensional lines repeating. But now we have what we have is planes. So planes of atoms that are actually stacked. Okay, and the process by which light is monochromatized is also different from the actual diffraction grating that people make. So in this nature-made grating, the principle is actually even simpler. What happens? So what happens is that the light comes in and then gets reflected by, guess what? By the law of reflection. So the incoming angle is the same as the outgoing angle, but let me actually warn you that in X-ray diffraction, in Bragg diffraction, we don't actually use the same convention as optical reflection, because these two different fields have developed in a different manner. So by history, we measure this angle as our angle. So it's a little bit weird, but well, the world is sometimes weird and inconsistent, and that's okay. So let's see. So that's phi, and then by the law of reflection, this is pi. So it's just a specular reflection. That's what it is. And so now, let's say your detector is collecting light right here. So the detector is detecting light right there. So then some light can come, in this path. So some light can come and hit the second plane here, and then go out, and follow the same path and get detected. So now, maybe some of you see the similarity of this setup with the thin film interference, except, this is, calling this thin film is really, an underestimation. This D is, on the order of 3 angstrom, 10 angstrom, and things like that. So that means these are atomically thin. So really, super thin. And also, notice that the angle here is not actually normal incidence. So in the thin film interference, remember that we just strategized to describe only normal emission, because non-normal emissions are somewhat complicated there. But here, we're not doing that. Here, the light is generally at an angle phi. So why is that? Well, because The reason is that if this was normal emission, then the incoming light and outgoing light, they will overlap, and you cannot get the setup to work in practice, because the outgoing light should be separated from the incoming beam. Also notice that this type of crystal has infinite lattice planes oriented in different directions. So what happens is that no matter in which direction you send the incoming beam, the different lattice planes will basically diffract in the direction that is appropriate for those lattice planes. So what will happen is that infinite number of diffraction spots will be generated just as at one go, and so so one gets these beautiful patterns, X-ray diffraction patterns, by doing so. So what you need to do is if the incoming beam is at a certain angle, what kind of spots you expect from theory, and then you need to go and place your detector at the right position to collect the light, wavelength of light. This diagram is a little bit cramped, so I'm going to go to the next slide and discuss this diffraction formula. Okay, so let's actually draw a better diagram than the one that we drew in the previous slide. One of the reasons why the diagram in the previous slide was not very good is because I drew it in such a way that this angle is 90 degrees by eye, and that's not a good thing to do, because it can confuse people. And so let's say the beam comes here and the beam goes out there. Just for the fun of it, I'm drawing the beam in the opposite direction to the one that I drew in the previous slide. Forgive me for that. Okay, so then in the second layer, you get this. So now the question is, what is the path length difference here? If you look at books, including our textbook and any other book, in order to figure out the path length difference, the standard thing that people do is, draw an equivalent diagram, but with a reflection point, in agreement in terms of their horizontal positions, and then you can draw two vertical lines there, and then the path length difference is right here. These two lengths, and so you can do that. But here I'm going to do it slightly differently, just to demonstrate that you can do whatever way you want as long as it's correct. So here, let's draw this triangle here. So a right angle there, and then let's draw that triangle. And the path length difference between these two rays of light that interfere at the output is basically given by, let's say this is x1, and then let's say this is x2, so that path difference equals x2 minus x1. Okay, so now we will make some observation here. The first observation is this is phi. And another observation is that this is a straight line here, so that means this angle and that angle is the same, so this is also pi, right? Well, there are many ways to see that this is phi. This angle, that angle should be the same because these are parallel lines and so on. So that means you can see that x1 x1 is x1 and x2. They have certain relationship. So if you look at x2 and x1, x1 is x2 times cosine of 2 pi. So that means x2, 1 minus cosine of 2 pi. And what is this? If you use the double angle formula, this is 1 minus 2 sine squared pi. So this is 2x2 sine square pi. And what is x2? Well, for that x2, let's draw a vertical line here, and notice that this this lattice spacing, let's define it as d. So that means this x2 sine phi is d. So that means x2 sine phi is d. So use that. Then we get we can get rid of one power of sine phi by re-expressing this 2d sine phi. So that path length difference is 2d sine phi. So that means Bragg diffraction condition. Remember, this is a grading problem with a huge value of n. So that means all we care about the principal maximum, because you know, other than the principal maximum intensity, which is huge and which is very low, which is basically a Dirac delta function peak for large n, there is no other intensity coming from this lattice plane. So all we need to care about is the principal maximum condition. So that's that condition corresponds to the adjacent two paths like this should constructively interfere. So the constructive interference between these two planes and these two planes, so that's the principal maximum condition. So that means 2d sine phi equals m lambda. That's it. That's the celebrated Bragg diffraction condition. One thing to note is that maybe some of you worry about pi phase shift and things like that when this light is reflected from the lattice plane. That's a valid concern. There could be a phase shift. However, notice that if there is a phase shift, that same phase shift should occur on the second lattice plane as well. So in terms of the phase difference between these two rays of light, that phase shift doesn't matter. So we don't need to worry about that. Another thing that I want to say is that I just said that when n is very large, this Bragg diffraction condition corresponding to principal maximum is the only thing that we need to worry about. Principal maximum condition is the only thing that we need to worry about, because when n is very large, that's the only place where the intensity is observed from this set of lattice planes. However, if n is not very large, so suppose you have a crystal of a very precious kind, you have only a very small crystal, microcrystal or even nanocrystal. If you have that, then depending on the size of it, n might not be very big. Maybe you have a nanocrystal where n is only 100, maybe 50 or something like this. That's possible, and you can still do the X-ray diffraction on that to solve for the structure and so on. When you do that, you will actually have to apply the grading formula the full intensity formula that we already studied, and then you will note that in that case, the diffraction peaks will have a finite width. So actually, that's what we're going to talk about: the diffraction, the general properties of these diffraction peaks as a function of n. Okay, so let's find some more fun facts about this diffraction intensity formula. And well, you by now you should be familiar with this formula. What is the delta? Delta is kd sine theta. But we just did the X-ray diffraction from crystalline planes. In that case, the angle phi was defined as pi over 2 minus theta. So it's just a different convention used in X-ray diffraction compared to optical experiments. In any case, we know this. Now I'm going to notice that this function, this fancy function here, is has been noticed by mathematicians as well. So what mathematicians did was they gave it a name. Well, mathematicians discovered this function at some point, and so so this f delta is what we call Fourier kernel, and it's got several properties. Its period is 2 pi as a function of delta. So how do we see that? Well, the denominator has a longer period. So look at the sine delta over 2. So that has a period 4 pi, but when you square it, the period becomes half of it. So that's 2 pi. And another interesting property is that when you go f delta and integrate it from delta 0 equals from delta 0 to delta 0 to plus 2 pi, so you integrate it over one period, and the value is 2 pi. So what it is that the average value of this Fourier kernel from angle 0 to 2 pi, or any 2 pi interval, is just 1. Okay, and then the third point is that when n goes to infinity, f delta becomes 0 if delta is not 2 pi m. So remember, delta equals 2 pi m is the principal maximum condition. So everywhere else the intensity is 0. So that means the diffraction pattern becomes basically a discrete function, spike function, and we have lots of spikes at principal maximum positions. Otherwise, the intensity is 0. So when this happens, we call this Fourier kernel just a series of Dirac delta functions. When I say Dirac delta functions, that delta doesn't have anything to do with this definition of phase shift delta. So please don't confuse the two. If you don't know what a Dirac delta function is, fine. I'm not actually saying that you need to know what a Dirac delta function is. It's just that at some point in your career, you will have to know that. So maybe hearing about Dirac delta function is not a bad idea. In any case, so this property 2 is extremely interesting. So this actually reflects the energy conservation. And this is how it goes. Remember that what it is that so IR is basically the intensity that comes from one slit. to a particular position on the detector. So IR is the property of one beam coming from one slit. And notice that if you integrate from, you know, in any 2 pi interval, then what you get is 2 pi interval, you get IR times n times 2 pi. So 2 pi IR is what you're going to get from one beam, whether there is an interference pattern or not. And what it shows is that the total intensity in any interval of delta, going from delta 0 to 2 pi, any 2 pi interval, when you integrate over delta, you get 2 pi IR times n. So this is what you're going to get from single slit beam, and the fact that it's multiplied by n means that you basically have the energy conservation. That's what it should be. Whether you have coherent beam or incoherent beam, you get diffraction patterns or no diffraction patterns in the case of incoherent beam. It doesn't matter. The total energy should be conserved. So when you integrate over 2 pi interval, this is what you should get. And here we have demonstrated it, the energy conservation principle precisely. Another thing to notice is that this Fourier kernel has so this is what we covered before, but I'm just going to emphasize it. Hold on a second. This diagram is not really good. Okay, so what you have, well, I don't know what's wrong with me. Let's see. So remember that for a finite n, as a function of delta, you get twice bigger peak here, and there's a principal maximum and then minimum intensity right here. And the difference between this, the distance between these two minima were given by 4 pi over n. So that means this width, let's say that's the width, and then there's this height. The height remember what it was? Height was actually n squared. And width, well, width is, you can define the width as full width half maximum, or the minimum distance like 4 pi over n. It doesn't matter. What's important is that width is on the order of 1 over n. It scales as 1 over n. So right there, see that when you can multiply height to width, you get a number which is on the order of n, and that's the area under that curve. And that area is, of course, order n because that agrees with this integral here too. This integral is the area, the total area, and total area should be mostly in the principal maximum peak. So if total area is of order n, then the area of the principal maximum peak should be also order of n. So that's this this discussion makes it clear that that's true. The fact that the height is n squared means that if you have large n, the principal maximum peak will become extremely bright, extremely intense. The fact that the light here has intensity going like n squared has to do with the fact that the beam that we are dealing with in this diffraction experiment is coherent. So just remember that when the intensity scales like n squared, That's the reflection of coherence physics. And the fact that the width here is on the order of 1 over n actually tells you something interesting. Remember in the crystal case, I was talking about nanocrystal and so on. So if you have a nanocrystal that you made, and then you wanna measure the size of it, how do you do it? Well, one thing that you can do is you can look at it under a nanoscope, like a STM or AFM and things like that. That's one possibility. You can also do X-ray diffraction, and if you do X-ray diffraction, the width of this peak will actually tell you the width of the width of your crystallites. So the fact that the width is on the order of 1 over n, or this width is 4 pi over n, can be used to measure the n value of your crystalline sample. And so if you have a very large crystal, then this peak will become extremely small, and extremely narrow and intense. If you have a lousy crystal, then this intensity will not be very high, it will be low, and then it will be very broad. So that's one way this diffraction peak line shape can be used to get really useful information.